So section 10.2 is talking only about chords, and in particular it's congruent chords. And so there are only two theorems to worry about this time, and they are so similar that the given or the premise for one is the conclusion for the other. So let's look at a circle, and let's say we have chords here, and we'll call this guy A, B, and we'll call this guy C, D. All right, so let's say that these two chords are equidistant. From the center of the circle. So chords are equidistant. Remember back, equidistance, an old word we've used in the past, equi being equal, distant being distance. So if two chords are equidistant from the center of the circle, to measure their distance, we draw a line perpendicularly from the center to the chord. That doesn't look very perpendicular, does it? Something like that. So these chords are equidistant. If this is the center, then this line and this line are congruent to each other. So if two chords are equidistant from the center of the circle, then the chords are congruent. So AB would be congruent to CD. Likewise, if two chords are congruent, then I'm sure you could draw the conclusion already. If two chords are congruent, then they are equidistant from the center of the circle. Okay, so keeping those two theorems in mind, let's go ahead and try a couple examples. Let's do an algebra example first. So we've got a circle here, and here's a chord, and here's a chord. And we'll call this guy A, B, and this one is C, D. And we'll call this circle O, and this is point P and point Q, perpendicular. Okay, so we are given circle O, and that AB is congruent to CD. We also know that OP equals 12x minus 5, and OQ equals 4x plus 19. We're going to find OP, which means first we need to know x. We know that the two chords are congruent, thus they are equidistant from the center. So that means OP is congruent to OQ, and we can take their expressions and set them equal to each other. All right, so now we've got some just elementary algebra. You can handle this very quickly and find that x equals 3, and then OP, substituting x in, 12 times 3 minus 5, or 31. All right, so there's an algebraic example. Let's do a proof, since we're back into the swing of proofs. Here's our picture. It's a circle And here's a chord. Oh, there's the center. There's a chord, there's a chord. There's a line, and a line. And we'll draw some right angles here. And this is A, B, C, circle P, there's Q, and R. So we are given triangle ABC is isosceles. And the base is AC. We're also given circle P. And PQ is perpendicular to AB. And PR is perpendicular to BC. Excuse me. We're going to prove that triangle PQR is isosceles. Okay, so since this is an isosceles triangle, we know that AB and BC are congruent. So AB is congruent to BC since triangle ABC is isosceles. Alrighty, if they are congruent chords, then we know they are equidistant. So that means that since chords are congruent, they are equidistant from the center. P. Thus, actually I'll do a comma. Thus, PQ is congruent to PR. So that's congruent to that. Well, hey, we've got an isosceles triangle then. Therefore, triangle PQR is isosceles since two sides are congruent. And there we go. Not a problem. Now, as you're doing your homework, keep in mind you are able to draw lines like radii or perpendicular lines wherever you want or need. So that's just a little hint. When you get stuck on any problem, give that a try. All right, I will talk to you later.